Hey everyone, and welcome to today's Explainer. Now, if you're joining me, you already know that in the world of industrial and commercial engineering, the details absolutely matter, like a lot. Today, we're zooming in on a choice that honestly might seem kind of straightforward at first glance, but it actually carries massive stakes for your entire infrastructure. We're talking about the showdown between perforated and solid bottom cable trays. Getting this wrong? Well, it can lead to catastrophic thermal failures, structural buckling, or just severe electromagnetic interference. So we're going to unpack the real science and the strategy behind this exact trade-off so you can specify your next project with total confidence. So think about this for a second. Are you risking ampacity or are you risking protection? Because that is the fundamental tension we're dealing with here. When you specify a cable management system, you're forced to prioritize what your cables actually need most to survive in their specific environment. This seemingly basic structural choice has huge consequences for cable safety, system integrity, the whole shebang. You are literally acting as the architect of the cable's microenvironment. Okay, here's our quick game plan for today. We'll start with the core dilemma, move into managing heat and ampacity, then look at ingress and EMI shielding. After that, we'll hit structural strength, give you a practical decision guide, and wrap up with the global industry standards you need to know.
All right, let's dive right into part one, the cable tray dilemma.
You know, every great engineering decision is basically just about managing critical trade-offs. You almost never get to have everything perfectly all at once, right? So on the left side, we've got the perforated tray. Its entire existence is optimized for heat dissipation and maintaining ampacity. It literally lets the system breathe. But, and here's the catch, if you choose that thermal venting, you inherently sacrifice what's on the right side, the solid tray's strengths. A solid tray is your fortress. It's kind of like choosing between a breathable athletic shirt and a heavy-duty raincoat. If you absolutely need a fortress to block out the rain, you can't exactly have wide-open windows. That right there is the foundational showdown of cable tray selection. Moving on to Section 2, Managing Heat and Ampacity. So heat buildup. It is easily one of the most common and frankly dangerous failure points in electrical infrastructure. Cables generate heat when current flows through them. We all know that. And if that heat has nowhere to go, you've got a major problem on your hands. Now check out this specific range, 30 to 50%. When we talk about perforated trays, we aren't just arbitrarily poking random holes in a sheet of metal. Engineering data actually dictates that a perforation open area of 30 to 50% is the exact sweet spot. It's the specific metric required to get optimal airflow around the cables, letting the heat escape, but without totally compromising the physical floor those cables are resting on. And the reason that 30 to 50% open area is so crucial is that it directly lowers the cable's surface temperature. Why does that matter to us? Ampacity derating factors. Ampacity is simply the max current a conductor can carry continuously without exceeding its temperature rating. If a cable gets way too hot because it's trapped in a solid metal box, well, you have to derate it, meaning you literally have to run less current through it just to keep it safe. By letting those cables breathe through a perforated base, you stop them from overheating, which ensures they maintain their full intended current carrying capacity. All right, let's flip the script and look at Section 3, Ingress and EMI shielding. Because honestly, what happens when heat isn't your only enemy? In really harsh environments, the air around the cables is actually far more dangerous to them than their own self-generated heat. And this is exactly where solid bottom trays step up to provide critical defense. First up is ingress protection. Think about a heavy industrial plant. Dust, debris, dripping liquids, corrosive elements. A solid bottom physically blocks that stuff from ever reaching your vital cables. And the second point here is just as critical, EMI shielding. Electromagnetic interference can completely wreak havoc on sensitive data and communication lines. A solid metal tray acts as a barrier, shielding those cables from outside electromagnetic noise that could easily corrupt your data or disrupt control signals. So when the environment is hostile, going solid isn't just an option, it's absolutely necessary. Which brings us to Section 4, Structural Strength and Load. At the end of the day, whether you choose a tray with holes or one without, it fundamentally acts as a bridge. It has to structurally support massive, incredibly heavy cable loads over long distances, day in and day out, without just collapsing. To really get this, we need to talk about UDL capacity, uniformly distributed load. This is the maximum, evenly distributed weight that a tray can safely support along its length without failing. Cables aren't usually dropped in as single massive point weights, right? They run continuously. So calculating that UDL capacity is totally essential to make sure the tray won't just buckle under the sheer continuous weight of all that copper and insulation. Building off of UDL, we have to look closely at the actual physical design of the tray's base. The base construction determines what structural engineers call the section modulus. And section modulus is really just a geometric property that measures how much a structure is going to resist bending. Whether your base is solid or if it has 30 to 50% of its metal removed through perforations, that fundamentally alters its section modulus. And that directly impacts both your UDL capacity, how much weight it can physically hold, and the deflection, which is the sagging at the span between your support brackets. You have to engineer the material thickness and the profile to compensate for whichever style you end up choosing.
Let's get practical. Section 5, our decision guide. Okay, we've covered the physics and the trade-offs. Now, let's translate all of that into your next spec. On one side of the matrix, you've got data centers and commercial buildings. In these spots, you're running massive amounts of power and data, but usually in really climate-controlled environments. Heat dissipation is the absolute top priority here, so perforated trays are highly recommended. Now, look at the other side. Industrial plants and high-interference rail transit. Rail systems deal with huge electromagnetic noise from the trains, and industrial plants have dust and flying debris. In those spaces, protecting the cables from the outside world takes priority. That makes solid trays the clear winner. You basically just match the tray type directly to the facility's environment. But here's a pro tip, a bit of a rule breaker realization. You don't actually always have to pick just one. In really large installations, you can strategically mix trays. Step 1 is simply to assess your zone-specific risks. Literally walk the theoretical path of your cables. Are there certain zones with high exposure, and then others that are purely heat risks? Step 2 is executing the transition. You can actually run solid trays in the harsh, exposed zones of a facility, and then purposely transition over to perforated trays the second those cables enter a clean, climate-controlled area. It's all about strategic application to maximize both protection and ampacity.
And finally, Section 6, Global Industry Standards. Because let's be real, a brilliant design on a blueprint is completely meaningless if the product can't actually hold up in the real world. That's where rigorous global benchmarks come in. Take Xinma, for example. When they manufacture these tray systems, they have to comply with a strict alphabet soup of global standards. We're talking IEC 61537, NEMA VE1, BS EN 5085, and GB 312051. These aren't just fancy labels on a box. They are hard guarantees that whether you're relying on a perforated tray for its thermal dynamics or a solid tray for its EMI shielding and section modulus, the product is going to perform exactly the way it was engineered to. Furthermore, managing these really complex trade-offs usually requires a completely holistic approach. It's almost never just about the tray itself. Xinma actually manufactures complete systems. They don't just hand you a cable tray, they provide the busway, the vital seismic bracing to keep the whole thing stable during an emergency, and even intelligent cable management solutions. Having that comprehensive scope is really what allows engineers to confidently outfit super demanding environments like data centers, rail transit, and heavy industrial plants. So as we wrap up this explainer, I want you to mentally walk the floor of your own current facility or maybe that next big project you have coming up. Look up. Are your cables breathing right now, or are they shielded? Have you made a deliberate, calculated choice to optimize for ampacity derating, or did you build a fortress against ingress and EMI? Truly understanding this engineering trade-off is the key to making sure your infrastructure is safe, efficient, and built to last. Thank you so much for joining me on this deep dive today. Keep evaluating, keep optimizing, and never stop learning.